Okay, hello everyone, and welcome to the Trenchless Technology webinar series. My name is Jim Rush, editor of Trenchless Technology, and it's my pleasure to introduce our presentation called Direct Pipe Trenchless Method, Overview of Feasibility, Engineering, and Construction, with case study examples for practical application. Today's webinar is sponsored by GeoEngineers, Inc., and is presented by Jon Robison, PE and Principal Engineer. So we'll hear about direct pipe from Jon, but just a little bit of background. It was first introduced in Germany in 2007 and has developed into a unique and critical option for steel pipeline installations. In 2020, the worldwide total of direct pipe installations is on pace to surpass 150, with roughly 1/3 of these in North America. It's been used to install 30 to 56-inch diameter pipe with distances over 6,000 feet. So Jon will present the method and technology in more detail and share its advantages, as well as discuss some potential applications and risks from a trenchless and geotechnical engineering perspective. As far as Jon's background, he is registered in 15 states and has been providing trenchless and geotechnical project management and engineering services on pipelines and other projects across the U.S. since 1997. He holds bachelor's and master's degrees in civil engineering from the University of Rolla, and his projects range in size from single crossings of a few hundred feet to long, multi-state greenfield alignments with numerous trenchless crossings. So he began working with direct pipe technology in 2010 with the goal of helping clients understand the technology's benefits and limitations and developing appropriate design criteria for the method. Since that time, he's led engineering and construction teams on many direct projects in the United States and Mexico, and has authored or co-authored over a dozen peer-reviewed technical papers on the subject of direct pipe and other trenchless and geotechnical engineering topics. Additionally, he is a board member of Louisiana Tech's Trenchless Technology Center and currently chairs the ASCE Task Committee, which is writing a new manual of practice for direct pipe. So one exciting thing about today's webinar, we're pleased to announce that we have more than 470 registrants from 34 different countries. So following the presentation, I'd just like to announce that we'll have a question and answer session. And we encourage everyone to participate in that by typing in your questions into the designated panel. You can type in your questions at any time, and we'll address those following the presentation. So now I'd like to welcome our speaker, Jon Robison. Jon?
Thank you, Jim. I appreciate the introduction and the opportunity to present on your platform. I'm getting a little feedback. I don't know if maybe you could mute your line there. I'd like to thank also all the attendees. I appreciate you taking your time out of your day to join us here. As Jim mentioned, the turnout for this is really great, and it's an honor for me to get to speak to all of you. We've got a lot of ground to cover, and I'm going to try to leave some time for questions, as Jim mentioned, so let's jump into it. We like to start our presentations with a safety moment. I know this picture sort of looks like maybe like a Photoshop thing that you might see passed around on email with the guy's feet sticking out the back of the pipe. But it's actually a photo of a team practicing a confined space rescue scenario. So the safety moment aspect is when you recognize that you will have critical life safety operations in construction. Plan for them, prepare for them, and practice your response. Plan, prepare, and practice. Anything you're able to do up front in this regard will decrease life safety risk during construction. Okay, two more things to point out before we leave this slide. First, as a point of interest, it's common practice in direct pipe to have personnel entry of the pipe for diameters of 42 inches and greater. This is something for the project team to consider early in the planning phases of a project and to seek alignment from the owner and other stakeholders. Second, if you look in the lower left-hand corner of the slide, you'll see a paper reference. This is a good paper on direct pipe construction safety that was written by some folks who were at Laney at the time. As we go through the presentation, here and there I've noted references for further study, and I'll provide the full reference info for those at the end of the presentation. So if I'm talking about something that's interesting to you and you see a reference on the slide, jot it down, and again, I'll provide the full info at the end. All right, so as far as what we're going to cover in this webinar, the general categories of information are summarized here on the slide. I'll say that I took some time to review the attendees' comments and initial questions, and there's a wide range of experience and interest in our audience here. So everything from requesting general info on direct pipe, even what is direct pipe was a direct question, to questions on feasibility, potential applications of the technology, requests to compare it to HDD, to some questions wanting really detailed technical information, like how to calculate a hydraulic fracture factor of safety, or how to evaluate pipe stresses during installation. So I'm going to attempt to straddle that range of experience and expectation and start with some general information, but my goal is to get well past the introductory stuff and at least a little ways into the weeds on some of the topics. As Jim indicated, if you have questions as we're going on, please submit them and we'll get to them at the end. Okay, so what is direct pipe? That's a good question. This cartoon shows in a simplistic fashion the primary equipment involved in a direct pipe crossing. On the far right of the screen is the microtunnel boring machine. This is a more or less conventional MTBM. It's connected to the pipe thruster machine on the left side of the screen by the jacking or thrust or carrier, casing, whatever you want to call the installed steel pipe. The pipe thruster is the key, sorry, I had to get that picture to come up. The pipe thruster is the key innovation developed by Heron Connect in the early 2000s. That makes the whole process happen by gripping the outside of the pipe and thrusting it into the ground. This allows for prefabrication of relatively long pipe string or strings, depending on available workspace behind entry, so behind the pipe thruster. In front of the pipe thruster, the ground is excavated essentially as a curved microtunnel. It is a continuously cased, relatively low annular pressure, one-pass system, assuming no problems occur during construction that require pullback. Behind the pipe thruster, prior to launch, the pipe is strung, similar to what you'd see on the exit side of an HDD project. So the pipe thruster enables the installation and sits in the confluence of those two methodologies. So let's look at how direct pipe compares to other technologies, and I promise this will be the last cartoon for a while. But the direct pipe is the green line, starting closer to the ground surface, but working our way up from the bottom of the page. HDD, represented by the gold profile, typically has to be deeper and longer than a minimum length direct pipe. This is because the HDD hole is uncased during construction, and the fluid pressures HDD requires to move cuttings out of the uncased hole are much higher than you see in microtunneling or direct pipe. And some direct pipe profiles mimic HDD profiles, and we'll show an example of this later. But as a minimum requirement, direct pipe can be much shorter than HDD. So that's HDD. Comparing direct pipe to conventional microtunneling, the red line, direct pipe has the ability to launch and exit at or near the ground surface, eliminating the need for deep shafts shown on the microtunneling profile. The microtunnel would also typically be installed joint by joint cartridge style, as opposed to having the ability to have long prefabricated pipe strings with direct pipe. So looking at the history of the technology, as we said, it's developed in the early 2000s in Germany by HerenConnect. We had our first installation, Jim mentioned, in 2007, and the technology has sort of picked up incrementally through the years, with the year of the installation is on the x-axis and the number of completed projects is on the y-axis. So the green diamonds represent cumulative total projects. So in the middle of 2020, so this blue square in 2020 it represents about halfway through 2020. The total cumulative projects exceeded 150. If we look at that data a little bit differently, so this graph plots all of those 152 crossings with respect to the diameter of the MTBM on the y-axis and the length of the crossing on the x-axis. And we see that there's sort of a preponderance of the installations have been in the 800 or so feet to 2,500 feet or so, 42 and 48 inch. So I don't know if that's because there was more 42 and 48 inch pipe going in the ground, or if that just is a real sweet spot for direct pipe, but I thought that was interesting to note the amount of data that's clustered in that area. If we draw in an HDD minimum length line, so this would represent using conventional radiuses and minimal tangent lengths, what the minimum length that you could design an HDD conventionally. Everything to the left of that line would be below an HDD minimum length. So we're going to talk about how direct pipe can go shorter and shallower than HDD. We already mentioned that, but that graphically illustrates that more than half of the crossings, I'd say, I haven't counted them up, but just looking at the graph, more than half of the crossings completed to date would be shorter than an HDD minimum length. Okay, so let's look at some of the equipment. And by primary equipment, I'm referring to the microtunnel boring machine and the pipe thruster machine. So let's look at some of that equipment and how it's configured in the launch workspaces. This slide shows 4 different microtunnel boring machines that were used on direct pipe projects with rock and mixed face conditions, cutting wheels in the top of the screen, and more of soil sorts of cutting wheels in the bottom of the screen. This is a 750 metric ton pipe thruster on a project we worked on in central Pennsylvania. And you can see in this case, we're launching through an oversized launch casing. So the yellow building in the background is the control cab. And then right at the edge of the launch casing is the launch seal, the white apparatus with the black rubber gasket. And so that's another piece of critical equipment. But this is a 750 ton machine. If we kind of look more closely at the pipe thruster clamp, and this is a project we did in Texas, we see that the little rubber pads that are articulated on that grip the pipe, that's what provides the gripping force that allows the large hydraulic cylinders to thrust the pipe into the ground. This is a 500 metric ton machine on a project we worked on in Chicago, and it's on that subject. It's important to note that these are metric tons, so they're not the same as U.S. or short tons, and so just something to note when you're doing your calculations. This is an example of a 3-sided pit launch. It's a project that we designed in Louisiana, and this is a little earlier on in the equipment setup phase. The thruster clamp's not on, the launch seal's not on, but you can kind of get a feel for how the launch pit setup looked. And we see this pretty commonly in launch setups. It's particularly, depending on the topography behind the pipe thruster, it can reduce the amount of pipe handling equipment required. This is an example of a four-sided pit launch. We had to get a little deeper here to get under the interstate that's in the background of this picture. The track hoe that you can see in the distance is actually excavating the exit pit. So this was a relatively short crossing, and we had to get pretty deep pretty quickly to get again under that interstate. We didn't have a lot of room behind us in this case because the valley of the Delaware River was just behind the photographer here. Here's a few more pictures of that same setup, and you can note in the bottom right-hand corner, we actually used Permalock pipe in a segmental installation, joint by joint. That's the only use of Permalock on direct pipe that I'm aware of. This is a project, I showed the picture of the 500-ton machine earlier. This is installing 36-inch casing through a, 36-inch pipe through an oversized launch casing. And it's a good shot of the pipe seal there with the lubrication fluid port hooked into it. And we'll talk more about the different fluid systems involved in the process. This is a project in Texas, a nice overhead shot that gives a feel for the launch workspace, transitioning back into pipe handling in the stringing area. Again, another three-sided launch workspace. This is kind of a panoramic view of that same workspace. The site was really tight. We did not have a lot of room to work in, and you can see in the background of this picture, actually the fluid recycling setup is in front of the launch pit in this example. It's usually located about halfway back in the pipe string. So this was, because of the congestion of the site, sort of an unusual equipment setup was required. So the slides I've shown so far have been Heron Connect equipment. As we said, the initial creators of the method. We're also aware of another company in Germany that has the pipe pusher machine, and we're aware of a few of those projects in Europe and Africa. To my knowledge, that equipment is not in North America yet. Okay, so talk a little bit about the other systems that are involved in a direct pipe crossing. During construction, it's important, of course, to know where your machine is at. So there's really three primary location control systems. There's the water level hose that's connected to a manometer that measures your elevation. There's a measuring wheel, and that actually just measures the amount of pipe in the ground as it's pushed into the ground. And then the gyroscopic compass in the machine gives you your left and right values from center line. It's important to do checks of these systems with actual in-pipe surveys, and we'll talk more about that in a little bit when we get into the construction part particularly. But this is the primary location control systems. So we mentioned the lubricating fluid system. It's one of two fluid systems for direct pipe, and we mentioned that it's introduced at the launch seal. It's also introduced through joints in the microtunnel boring machine through lubrication seals. So you get it introduced two places, behind the cutting wheel in the annular space. So the cutting wheel will cut 2 to 10 or more inches beyond what the pipe jacking radius is, and then you get this lubrication fluid introduced to fill that annular space. The second fluid system is the slurry system. It's completely separate and independent of the lubricating fluid system. This is the system that takes water or engineered drilling fluid to the face, mixes with cuttings, and then pumps the soil and fluid back out to the ground surface to be recycled or disposed of. So this is a shot of the umbilicals being set up in a half can. The white racks are on wheels, rubber wheels, so they slide in and out of the pipe. The two long gray pipes are the slurry feed and return lines, and then the little white hooks are where the contractor will run power and air supply and guidance and other things from the ground surface to the machine. The rails there are actually where the wheels go for the personnel entry sled that runs up and down within the pipe to take personnel typically to the MTBM or to wherever they need to go within the pipe. This is a view from inside the pipe with all those systems installed, and I did not take this picture. So, this is a shot of the slurry fluid recycling. It's similar to what you might encounter on an HDD project with shaker screens and the roll-off bins for the cuttings. Additionally, in the background, you see the ultrafine centrifuge. That's a common sight on a direct pipe project and on some HDDs, but that's something that's pretty common to see. So we looked at the launch workspaces and kind of got a sense for what's required there in terms of space and what equipment is there. One of the advantages of direct pipe is the relatively limited workspace and equipment that's required at exit, typically. And we'll look at a couple of examples where a little bit more work was required at exit, but typically it's relatively limited. It can range from just digging a shallow pit and waiting for the machine to show up to a shored pit recovery, similar to what you might see in a microtunnel. And again, I think probably the only reason you would see something like this is if your design geometry required this. You typically can, if you have flat ground, just allow the machine to continue to come up to grade and exit something more like this with a ground surface sort of recovery. Is another good example of ground surface recovery, and you can see when the machine does daylight, there is some workspace required. You've got a track hoe there and a small crane and some trucks and things, but you could typically not see much work at exit other than maybe putting some timber mats down for most of the drive, and then only when the machine was getting close, go over and prepare to receive it. Another area that we're seeing direct pipe having a lot of application is in shore approach, and it tends to be really almost head-to-head. It can compete with HDD on cost with shore approaches. So with other applications, it typically fits into a notch where for one reason or another, the HDD approach isn't going to work. But on shore approach, we're seeing that direct pipe can be fairly competitive. And the main reason for that, I think, is that there's just really a lot less marine support and equipment required over the length of the drive, over the length of the construction window at exit in the water. So. Okay, so let's look at some planning information. Some common applications that we see in our practice anyways, we mentioned the short and shallow crossing desired or required. Again, that's relative to HDD. It's most often compared to HDD, at least in our experience. The low installation fluid pressure, we mentioned that, and that's really a strong market that's developing for direct pipe, and we'll talk about one that we did because we couldn't get the HDD permitted. We couldn't meet the required factor of safety against hydraulic fracture with HDD, and so we went to a direct pipe, and so we're seeing more and more of those crossing under predominantly levees, but the same principles would apply to any sensitive surface feature. We've also designed a number of them in gravelly soils or weathered bedrock, things that you look at from an HDD perspective, and you think of hole stability risk or settlement risk or other things that it looks a little dicey or even unfeasible for HDD. Direct pipe is a pretty good application there. And then we mentioned shore approaches. So this is a pretty good graph that we've developed for the draft ASCE manual of practice, and I'll just give a quick update on that. We've gotten most of the writing done on that, and it's right now in a peer review process with our Blue Ribbon Committee. We hope to be done with that by the end of the year, and time to have a workshop at ASCE Pipelines next year in Calgary, and hand the physical book out at that time. So I guess that would also be dependent on if we can all meet again in person, but that's kind of our goal as we work through this through the manual practice process. But so this graph has appropriate geology on the upper y-axis, or upper x-axis, excuse me, and pipeline diameter on the y-axis, and tunneling distance on the lower x-axis. You can see that the smaller diameter machines are capable of less length and less tough ground conditions. So really, to get into rock sorts of conditions, you're looking at a 42-inch machine, and really to get out to those distances in excess of a few thousand feet, you're also looking at a larger diameter machine. And of course, we saw the slide that 6,330 feet, I think, was currently the longest direct pipe that's been completed, and this graph shows that we think we can go farther. But we just haven't had the project yet to do that. But I want you to keep in mind, I guess, on the far right of the appropriate geology, you know, we kind of have a limiting condition there at 200 megapascals of unconfined compressive strength in our rock, and so keep that value in mind. We're going to look at that a little bit in more detail here in a minute. So another important part, or really critical part in our perspective to having a successful direct pipe or any trenchless installation, but sort of we're talking about direct pipe today, is the geotechnical due diligence, and that's considering geologic hazards, scour depths, undermining, karst, things like that, doing a robust geotechnical exploration. Something that would be, if you're familiar with microtunneling standards and microtunneling exploration, something that would be probably closer to that than what you might see on a typical HDD. So more samples, tighter spaced borings. Characterizing the groundwater is important, particularly if you've got entry and exit pits. We want to do a robust suite of soil laboratory tests. And if we're in rock, we want to do rock laboratory tests as well. The failures that we're aware of, or even the projects that have significant problems, nearly all trace their roots, and by significant problems, I'm talking about significant budget overruns or schedule overruns. Those nearly always trace their roots back to not having a full understanding or appreciation of the geotechnical conditions at the site. So can't stress that enough, to spend $1 on geotechnical work up front and save $5 or $10 in construction. So important. Okay, so talking about the rock, I wanted to bring this up because I know it's been an issue on some projects. So we said 200 megapascals was sort of a limiting value. So if we look at that and draw a line, you see the green line I just drew there on the screen, and that's just one piece of the puzzle. I think it's important also to look at the abrasivity of the material. So you could have a rock that's 150 megapascals and a Curvature index of 2, and feel pretty comfortable about getting through that in a relatively short amount of time, and without perhaps having to retract the machine to change out cutting tools. Or you could have a rock with an unconfined strength of 150 megapascals and a Curvature index of 5, and you could be pretty worried about being able to get through it, or at least get through it without having to retract the machine. So something that we don't always see is abrasivity index testing, but it's something we definitely encourage, particularly if you're looking at metamorphic or igneous rock, or something beyond a real soft sedimentary rock. Okay, so let's look at a couple of design examples, and just to give a flavor for kind of what we've seen the direct pipe method used for. This is a project I showed some pictures of before in Louisiana, and I realize the details are hard to see, but I just want to give a flavor for the project. So this is 850 feet long, 42-inch diameter. This is an example of sort of more of a minimum length and depth crossing, similar to what you might see out of a microtunnel, a curved microtunnel. It's a 3-degree launch angle with 4,800 feet radius, and the pipe goes to an intermediate vault, which is right in the middle of the profile. So from the intermediate vault, the pipe slopes at a constant 0.5% back to the other side, to the right side, the east side of the crossing. And that's so that this was an industrial owner, and that pipe, it was a steam pipe, needed to be able to drain to that interior vault when they were doing maintenance. So we've got aspects of, we're turning a radius, we've got a constant slope like you would see perhaps in a microtunnel. We're about 15 to 18 feet below the interstate, and we're exiting in a short excavation, a 17-foot deep short excavation. So this would again fall into the category of minimum length, minimum depth sort of HDD. This crossing was designed more on an HDD like profile. In fact, it was an HDD, initially proposed as an HDD, but we could not get the factors of safety for hydraulic fracture to work out for it. So this is a 3,500 foot 48-inch. The curvature on the crossing is 6,000 to 10,000 feet radiuses, and there is some combined curvature in there. We had to put combined curvature in there to avoid the navigation bollards in the Sabine-Neches waterway, which is the big waterway on the right side of the crossing. So that's the third heaviest trafficked waterway in the U.S. And so we're crossing that. We're crossing a pretty big railroad yard, and perhaps most importantly, from a permitting standpoint, we're crossing the hurricane flood protection levee at the left-hand side, or the near entry of the crossing. So this was the first direct pipe crossing permitted by the Corps of Engineers to cross under their levee, and we'll show some more slides on it later because it's an interesting example. So let's dive a little bit into the engineering topics that folks had asked about. And first we'll look at estimating the jacking or thrust forces. We're looking at that same cartoon again. And this is normally the audience participation part of the presentation that I do. But since you can't talk to me, I'll ask and I'll answer the questions myself. So the question is, when during the drive does the maximum load occur? And the picture is sort of a clue to the answer there. So theoretically, the maximum load occurs when you're just about ready to punch out, so you still have a face pressure portion of your load, and you have the full length of the pipe in the soil picking up skin friction. So the whole length of the pipe back to the pipe thruster, it's all picking up load as it goes through the soil there. And then the second question, so that's the answer to the first question. The second question, where is the maximum load? And what we're concerned with there is, where is the maximum load? Where does the pipe feel the maximum load? Because we're interested in the stresses on the pipe during installation. And the answer to that is, it's at the pipe thruster. That's where the maximum load occurs during installation. So back in 2014, we looked at the time, most of the direct pipes, or several of the direct pipes that had been installed, and we came up with this graph relating the thrust force per circumferential area of installed pipe. So that's all the steel touching the ground in the hole. And then we related it to both the kind of soil types and the length of the installed pipe. We developed this graph. And surprisingly, at least to me, and this is kind of a limited amount of data, so take it for what it's worth, but surprisingly, there didn't appear to be a correlation between the different soil types and the thrust forces needed to move the pipe through those soil types. The other thing we saw is roughly 20 to 40 PSF would encompass most of the range of loads, with 40 being there's two sort of outliers that are up there, and then most of the crossings were around 30 PSF or less. Drew Sparks and Rob Hutz put a nice paper together in 2019 that included some of this information, and then went beyond that and included some additional good information as well. So if we've developed our load, and I see we're at 140, so I'm going to speed up a little bit here. So we've developed our load, and we plot that on a graph like this, and elevation is on the primary y-axis, station on the x-axis, and thrust force on the secondary y-axis. And it's important to realize this is a snapshot in time. So this is the load. This is, if you're used to looking at microtunneling data and the load incrementally increases as the crossing is installed and goes up to the right, that's not what this is. This is a snapshot in time at the maximum theoretical loading in the pipe. So that's what we're trying to capture here on this graph. So we convert that load to a stress, And then we also calculate the bending stresses based on the radius, the allowable radius, typically not the design radius, but the actual allowable radius, so what we're going to allow the contractor to do during construction. And we developed this graph, including hoop stress. And again, we've got elevation on the primary y-axis and stress on the secondary y-axis. And this one is fairly complex. If you recall, we had horizontal curves, vertical curves, and combined curves, and that's why the bending stress sort of looks choppy. There's a lot of different curves in there. So we've got our loads converted to stress, and then we take those stresses and we compare them to the allowable stresses, and we develop a capacity analysis graph, is what we call this. So anything over 1 indicates that you have adequate axial or bending capacity. We also look at combined stress similar to an HCD, only a little different equations because you're in compression and not tension. And that's that orange dashed line that shows up below 1. So similar to an HDD, combined stress, you need to be below 1. So that's really short introduction to the stress analysis. I've only got one slide on buckling, but it's important to mention that based on the principle of assuming that it's going to buckle down the hole, we don't really understand the soil structure interaction at depth very well. And some of these pipes, after we get done installing them, we're going to pressure them up to, say, 1,500 PSI for a gas line or something. So we really want to avoid any kind of steel capacity issues with the pipe. So we want to keep any buckling that occurs in the elastic range. In order to do that, and I don't have time to get into the details of why the math works out this way, but we limit the axial stress to 39% of the pipe yield stress. So an important note there on buckling. Okay, so let's look at hydraulic fracture. This is sort of a made-up scenario that Drew Sparks and I put together in 2015. But the soil types and the design are pretty typical of levee design you might see in the South somewhere, Louisiana or Texas. And in this case, you can see that our formation limit in green is pretty close to what we calculate as the applied pressures during construction, which is the red line. And it's certainly not twice the applied pressure. So that's not going to calculate to a factor of safety of 2. If we change it to a direct pipe and we calculate the pressures from both fluid systems, both the slurry feed and return systems, which we can actually run at or just slightly below the surrounding groundwater pressure. So that's how we figure that pressure. And the pressure of the lubrication fluid, which we calculate that assuming continuity from the ground surface and a drilling fluid unit weight down to the point of interest. So that's how we calculate that. And as you can see, when we divide those two together, we achieve the factor of safety of 2 that we're looking for. Okay, so a little bit on construction. And this is sort of from an engineering quality assurance documentation sort of perspective. There's kinds of things that we typically, the data we collect and process during construction. This is the this is the Sabine-Neches project that we mentioned a couple times. The red is the thrust force that was measured, and the blue is how much of that thrust force is at the face pressure. So I think that's interesting also. Sorry. also, when we think about how we calculated those forces in the pipe, and we assumed a green line, sort of like that, is what the load condition is in the pipe at the maximum theoretical loading. Although in this case we had the green line was, I think we designed the pipe to accommodate up to 1,000 tons, and we ultimately saw just a little over 400 tons of load. So we were pretty comfortable that we had more than adequate capacity there in the pipe, and that installation went very smoothly. So we also, in accordance with the permit conditions, monitored the annular pressures, and this graph, it has our original design calculations for annular pressures and also the pressures that we measured during construction. The blue sort of jagged lines there that kind of follow along the red curve are the actual pressures measured during construction. Those pressures need to be measured on a port on the side of the MTBM. You don't need to measure the pressures in the mixing chamber or at the face. Those aren't the pressures that we want to look at. We're zooming in on that data that we acquired during construction there. Felt pretty good about how closely that aligned with what we had estimated going into the process. So a couple slides here. Sorry, this is a different project. This is one we did in weathered bedrock, but you can see we're also going to look at horizontal location deviation with respect to whatever the standard or specification is. And I mentioned earlier the importance of doing an in-pipe survey to check that the data you're getting is good, and you can see here that we've had to correct the data by that survey process. So something to keep in mind. This is the vertical data, and we're showing the tolerance here, 12 inches above or below. And again, you see there's some errors in it. There's some corrections based on those in-pipe checks. And another example of thrust force loads, face pressure, and contact forces. Here we're looking at penetration rate and face contact force, and this information can tell you if your cutting tools are wearing out, or maybe you're in a new formation and you're all of a sudden getting a whole lot more production. But it's good to keep track of course, the penetration rate and production you're getting to see if your schedule is going to hold up. Okay, so some examples of things that we typically like to see in the construction record. The items in green are probably, I guess, priority items. And then the items in blue would be other useful information to document. Okay, so here's the reference slide that I promised, and I'll pause here. And looks like I left myself about 10 minutes, Jim, if we want to go to a question and answer mode.
Okay, yeah, plenty of questions have been coming in, and if you've not done so, please go ahead and submit your question. The one thing I did not mention is that any questions we're unable to address because of time during the live session, we'll address offline by email. So go ahead and get your questions in. So I'll just go ahead and get started, John, if you're ready. Some of the questions here. First of all, the question is direct pipe like a combination of HDD and micro tunneling?
Yeah, I've heard it described as, and maybe I've even described it that way myself, but I think a more nuanced answer would be it's like it's really a curved microtunnel in the way the ground is excavated in the heading of the pipe and the systems involved with the excavation and removal of the ground. And then it's like an HDD in the ability to string long sections of pipe behind the pipe thruster. So it is kind of a combination, but it really, if you had to say what's it more like, you would probably say it's more like microtunneling than HDD.
Okay. How does overcut size on this system compare to a standard microtunnel?
What we've seen is overcuts of up to 10 to 12 inches, and compared to and we've seen smaller overcuts as well, but a standard microtunnel, I think you would see overcuts of around an inch or two, much smaller. So the overcuts can run quite a lot larger here, and I think part of that is opening up more hole to push these things around curves is important. And then part of that is that you might have a smaller diameter pipe and you're pushing a larger diameter machine because you want the capacity of the big machine. For instance, one of the projects we did was a 42-inch pipe, but we really wanted to push a 48-inch machine. By the time you skin the 48-inch machine up to get the cutting wheel on it, you've got a 53 or 54-inch diameter hole that you're then pushing a 42-inch pipe through. So much larger in general, I think, is probably a fair statement there.
Okay, as far as curvature, is there a maximum curvature for a direct pipe installation? It also references a minimum bend radius. Can you speak about the curvature of it?
Yeah, I guess if I understand the question, there's not really a maximum. I mean, you can put them in straight, so I guess that would be a curvature of infinity. But as far as minimum, we typically will start out at 100D, similar to what you would see on an HDD. And then, as you might have to do on an HDD design, you might whittle it down a little bit from there. But a lot of it depends then when you start getting lower and lower about how your pipe stresses play out. And so on a long crossing, if you've got curvature at the start, you're going to have high axial loads, high bending stresses right at the start. And it probably, the numbers may not work out for you. So I think starting at 100D as a rule of thumb is a reasonable place to start.
Okay. So there's the cost questions that inevitably come up. How does the cost per foot compare to HDD and microtunneling?
Yeah. So it's kind of, in my opinion, there's a little bit of an apples and oranges kind of comparison. Where we've seen it in our practice, it's because we couldn't get an HDD to work. And so if you're already going somewhere where you can't have the one method, comparing the costs is difficult. You can compare them directly, I think, on the shore approach, as I mentioned. So there, I think direct pipe probably would hold its own in terms of a comparison with HDD. On land, conventional crossing sorts of things, you might be 2 to 5 times even what your cost would be if you could get an HDD to work. So it's hard to say, how long is it when you start talking about the cost per foot too. If you can go much shorter with a direct pipe, are you saving there versus a long HDD? So it's really tough to compare them, straight up, other than the shore approach.
Okay. What's the smallest diameter pipe that can be installed with direct pipe?
Currently, as far as the jacking pipe, and of course we've done a number of casing pipes that have had smaller diameter pipes put inside of them, or you could jack a casing pipe across and tie into a smaller diameter pipe and pull it back. But as far as what the machine jacks into the ground, 30 inches is the smallest that I'm aware of. I know that Heron Connect is working on 24 and 20. To my knowledge, those aren't commercially out there in the industry yet, but that's where the industry is heading, is more capability on the lower end, for sure.
Okay, and what's the best tolerance for installing gravity lines with direct pipe?
For installing a gravity line, I think I would tend to be pretty tight on the tolerance, and perhaps in the spec have a pipe must slope to drain sort of a note. I guess it depends on the elevations that you are starting and ending at, and if you only have a 0.5% to play with, then you've really got to be pretty tight on your elevations. If you're trying to drain something at 2% or 3% or something much higher, then you can allow, I think, the contractor to have a little more installation flexibility and still meet the slope to drain desire of the project. And I'll also say on that subject, the tighter those specifications are, the more often that contractor is going to have to get in and out of the pipe to survey the location and confirm and recalibrate the system in order to hit those very tight tolerances. So when you need a really tight tolerance, expect to have slower production and expect to pay more. But if you don't need it, then in my opinion, there's no reason to do anything more than say 2 feet, even if you don't need that. If you don't need that tight tolerance.
Okay. What types of pipe material can be used for the direct pipe method?
Currently, it's steel only for jacking pipe. Again, similar to the question about diameters, we have done several projects where we installed HDPE or other kinds of pipe within a casing. But as far as what's capable of withstanding all the installation stresses, right now it's steel.
And what is the minimum depth for a direct pipe?
I think it depends on what you're under, and it depends on the geology that you're in, and what your concerns are. But it would be comparable, I think, to a microtunnel, maybe 2 or 3 times the diameter. We typically want to be a little deeper than that, just for general comfort level. But I think, and again, it depends on how critical the thing it is you're under, and what the risks, what the geotechnical risks are. But 2 to 3D would be maybe a bare minimum starting point.
Okay. How about the use of GBRs? Would GBRs, geotechnical baseline reports, be important for direct pipe installations?
I think that there's, and we've talked about this in our MOP at length, because we've got a good group of folks, both from the oil and gas side, which is more my background, and the municipal side, where GBRs are common. And I think there's definitely space in the industry to use that tool. I think it's a good tool. I don't think it's been common so far, because most of the direct pipes that have been put in have been on the oil and gas side. But as we're starting to see more municipal applications, I would expect to start to see perhaps some GBRs associated with that work. It's a tool that the folks in that industry are very comfortable with, and they have a different contracting strategy than oil and gas, and so I think it would would be good to be able to look at that for sure.
Okay, you mentioned that steel pipe is used. This question relates to some other materials and the possibility. I mean, do you think it would be possible to jack concrete in the future and maybe some other materials as well?
I think it's possible to look at it. I'm not aware of any that have been done. I think it's, and I can't think off the top of my head, the stresses that those clamps, the rubber, those pads put on the pipe are pretty significant. And then with concrete pipe, you would ordinarily have, I think, like a kind of a bell and spigot kind of thing that you'd have to be able to get your clamp opened up enough to get around. So I wouldn't say it would be never a possibility. I just don't, at this point, I don't think it's been attempted or much has been done to attempt to try it. So.
Okay. As far as the conditions that the microtunneling heads can go through, can the cutter heads handle mixed face conditions such as alluvial deposits to a soft medium strength rock? Yes.
So it's a conventional microtunneling setup, and so anything that you could think of. And it has the same limitations and risks that as far as the mixed face and mixed reach conditions that you would have with conventional microtunneling. But certainly mixed face conditions could conceivably be tackled. You would want to avoid them if you could.
Okay. And how is the space between the pipe and the overcut addressed?
So that's what we talked about, the lubrication fluid. That's where that sits. If you were concerned, if your pipe was near the ground surface and you were concerned about settlement or something like that, we did have one project that we had ports in the casing pipe and we post-grouted the installation. But that's only direct pipe that I'm aware of that has done that. There may be others, but that's the only one I'm aware of. It's not a commonplace thing to post-grout. But if you're near the ground surface or underneath, critical piece of infrastructure and you need to do that, you can do it. It would have to be, I think, with casing pipe, unless you were, if you had a high pressure line that you were working with. But if it was a gravity sewer or something like that, I think you could put ports in that. So.
Okay. Are any internal supports, stalls, or spiders ever required for thinner wall pipes to resist crushing forces by the thruster?
I don't think anybody would want to attempt thin wall pipe with it. Just to be blunt. So I've never seen that, and I think the manufacturer would strongly urge not to do that, as would the contractors.
Okay. So can you talk a little bit about the mud system that's required to accompany this method?
Yeah, so as we mentioned, there's the two fluid systems. There's the bentonite lubrication fluid system that introduces bentonite lubrication fluid at the launch seal and behind the MTBM, and so that's what fills the annulus space. And then there's the slurry feed and return system that runs in the 5-inch diameter hose lines that we showed a picture of, the umbilical lines. And that essentially pumps fluid, just plain water or water mixed with something, to the microtunneling boring machine where it is introduced into the ground, mixes with cuttings, and then those cuttings are pumped back to the ground surface to a fluid recycling plant where they're run through sieves, the cuttings are taken off, and the fluid is recycled for reuse.
Okay, so what happens if midway you run into an unexpected hard metal object that was not located? Can you provide a bore that will go through any material, or what kind of mitigation measures could you do?
I think that, yeah, and we encourage development of a plan for the unforeseen, just like that. So what's your next option? And I think in that case, it would be, depending on how deep that obstruction was, perhaps you could dig a shaft and remove it. Perhaps you would have to pull your machine, retract the machine, and even grout the drilled hole in place, and then move over and start again. I don't think it's reasonable to think that the machine is going to be able to go through a large metal objects. I think that's I don't know that there's any machine out there that could do that. Depending on, well, I guess depending on the size and the width and everything of that metal.
Okay, so what dictates how much man entry is required, and how can man entry be minimized on long distance installations?
That's a great question, because we want to reduce the amount required, because there's some risk associated with it. And so there's really two categories of entries. And I've got a client that doesn't like them characterized as this, but for the purpose of this call, we'll call them planned entries and unplanned. And planned entries are, we're going to go in 200 feet when the pipe's 200 feet in the ground, and we're going to do a check survey to recalibrate all of our location control systems in our pipe. So that's a planned thing. And then depending on how tight the tolerance is, we're going to go in every 1,000 feet or 500 feet or 2,000 feet, again, depending on how tight those tolerances are, to recheck the position of the MTBM, recalibrate the location systems, and then and verify for ourselves that we're in the right place. So if you can make your tolerances very large or relatively large, then you can reduce the number of those entries. You can eliminate them altogether if you are not overly concerned about being, highly accurate in the installation. The unplanned entries are the machine breaks down, there's an electric short, there's a hose breaks, whatever happens in the MTBM that can be fixed from within the MTBM. And so when that happens, then a technician has to go in the pipe and work on it. Or you have to retract the pipe and all of the casing that you've got in the ground, or all the installation pipe you've got in the ground. So those are the two kind of buckets of entries. If we have an owner that doesn't want any entries in the pipe, and there's ways that you can design the pipe and use some sacrificial casing and do some other things to get an initial survey check, which you want, and plan to bring the whole thing out of the ground if you have a problem. And that's just part of the contract, because that particular owner doesn't want anyone in the pipe. So.
Okay, so we're kind of running toward the end of our time here, but one last question. You explained the guidance system, but how are the changes in direction affected? Yeah,
that's a good question. So I didn't show a picture of the machine operator, but in that control cab, person sits and actually steers the machine. And there's hydraulic cylinders in the machine that actually turn the angle of the machine with the front of the machine with respect to the rear of the machine. So it's articulated, and that's how the machine changes direction. It's not going to turn on a dime, and that's why the radiuses are as large as they are. But that's how those changes are accomplished.
Okay. Well, thank you. That brings us to the end of our time here. So I'd like to thank everyone for joining us today. I'd also like to thank John for his participation and GeoEngineers for sponsoring this session. Again, any questions we didn't get to in the live session, we'll address offline. And as a reminder, today's webinar will be archived at trenchlesstechnology.com. So if there's something you missed or would like to go back and refer to, that will be housed there. So thanks again, everyone, and we look forward to seeing you online again at a future webinar.